So if we take a look, last time we dealt with a strong acid HCl and a strong base titration curve. We showed that whenever you are mixing these again, you can basically, let's see if I can get this better. And maybe we just do that. Since these ionize completely, you figure out the concentration of the acid or base, whatever you have at the end of the system change, at the end of the reaction. In this case, we have 0.00144 moles of HCl. We got to find that concentration again. So we need to take the moles divided by the liters, and then we take the negative log of that to get the pH. Here, they were equivalent. So basically, we ran out of HCl and an AOH. That would give us a pH of 7. That's the equivalence point for a strong acid, strong base titration. If they're both mono. And then here, we react that and we end up with extra OH at the end. So we have to find the hydroxide ion concentration, and then we find the POH, and then we subtract that from 14 to get the pH. Now, the difference with this and an actual weak acid is whenever we titrate a weak acid, we form its weak base. So that's going to put us in a situation where we use Ka to determine the hydrogen or hydroxide ion concentration, depending on which one we're dealing with, weak acid, weak base, and use that to find the pH. So a few things about the curve. We'll take a look. This is pretty steady incline here. And then again, we have that sharp increase. Very, very big change in pH with very, very little change in addition of the base in this case. With this, we have kind of a steeper incline. And then we jump up here. Again, this is the equivalence point. Now, the biggest question, I believe, last time was, why is the equivalence point up here? Well, as we titrate that weak acid, and you'll need to make this change on there. It didn't make it for the final edit. As we titrate that weak acid, we are forming that that base. So that's going to bring the pH up higher. So what can you determine from this graph? Well, one, we have sodium hydroxide titrating acetic acid. What else? Well, what's the pH to start with? Yeah, 3 from the graph. What's the equivalence point? We take a look here, it looks like, so it's going to be halfway up this slope. Oh, what do you think? Halfway about here, between 8 and between 8 and 9. What else? What did it take us to reach the equivalence point? Between 20 and 25, we could probably narrow that between 23 and 24. What else? Louder? Created a basic solution at equivalence. Yep. And if we kept going, right, to see that plateau off. Let's take a look over here. These are both monoprotic, right? What do we notice about the equivalence point for the HCl and the NaOH versus the equivalence point for the CH3 and COOH and NaOH? They're the same basically, and that's because we have that, in a sense, that one hydrogen. There's a lot more we could get from this. If we wanted to, we could take and find the hydrogen ion concentration right here. And then with that, let's take a look. We know the concentration of this acid is 0.100 or 0.1, yeah, 0.100. If we take, what's that, 3, I'm thinking 3 is here. I'm going to go with 2.9. We take the antilog of negative 2.9. We find we get 0.001. So that's much lower than the 0.1, which is the concentration of the acid. Much, much lower. That tells us that this is definitely a weak acid. H plus concentration. If we wanted to, we could take this and divide it by 0.1 and multiply that by 100. And we'd see we get like 1.3% ionization. Right? We could go further on that, but that's probably good enough. Just with the graph, there's a lot of things that you could find. Again, this one's difficult to read. We don't have as many markings as we'd like. For your titration graph, instead of going like every 5 milliliters, you're going to go to every 1 milliliter. And then here, whenever you start to see that big increase in pH, you're going to change it to every 0.5 milliliter. So using the burette like we did last time. And you're going to want to make sure you get up here so you can see that plateau again. All right, calculate the pH of 25 milliliter sample of 0.100 moles per liter. A solution of CH3 being titrated in the above profile. So again, with this, we can use that MACA for the MACA, but we could also use the ice table. And since this is the first of these equations, it might be nice to see that CH3COOH break down. We add this to water. We're going to get H3O plus COO, CH3COO negative. CH3COO negative. And that's CH we lose right there. And with this, we are starting off with 0.100 moles per liter. Doesn't matter how much we have of that, 0 of that, and 0 of that. We're going to lose a certain amount of X here. So we're going to get 0.100 minus X. We're going to add a certain amount of X here and here. The same X we lost here because this is a 1 to 1 to 1 to 1. Then we get X and X. Up here, I'm going to go ahead and put the Ka expression. Ka equals H3O plus concentration products over the reactants. Why aren't we putting water in? What would water be? Liquid. 1. And we know we are trying to solve for this. So again, we are assuming that X is negligible. So we will have, we'll change the top to X squared over 0.100. Since it's negligible, we don't have to worry about subtracting that because it's going to be very small and it won't actually affect the significance of this number. The Ka is given to us 1.8 times 10 to the negative 5th. Now it's just a matter of putting that in our calculator. 1.8 times 10 to the negative 5th times 0.1, equation rearrangement, and then we take the square root of that. And we get that 0.00134. .00134. Actually, 13 would be good enough because we only have 2 significant digits there. That is the molar concentration of H plus. It's also the amount of the conjugate base we have here. So if we want the pH, all we worry about is the H3O plus. So we take the negative log of that. And as we said, it was close to 3 up here. We get 2.87, 2 significant digits. So the pH equals 2.87. Again, you could have used this formula right here if you recognized it. That is a shortcut. This is showing all the work involved. This is the acid constant. This is the molarity of the acid. Basically, that's this formula rearranged, the molarity of the acid constant, and then we square root both sides. All right, so now we have that acid, but we are going to take that acid and we are going to start titrating it. It says calculate the pH of 25 milliliters of the sample of a 0.100 molar same solution following the addition of 10 milliliters of 0.106 molar sodium hydroxide. Now the deal with this is we need a BCAA table. Basically, this is different than an ice table because we're having a reaction occur first. We're having this actually react with this. So let's see, CH3COOH plus NaOH is going to yield. Again, these are going to react to form H2O and then the CH3OO negative. Why didn't we bother putting the Na in there on this side? Because we could cross it out on this side as well. And that would be what we call the net ionic equation. What is the Na in this case? Spectator ion, right? If you wanted to put it over here, you could. But this crosses out all the spectators. This is actually what's going on in the reaction. All right, the second thing is in this, we can only use moles. So we need to find the moles. Why do we do this? Because what we're doing here is we're changing the actual volume. If we change the volume, what is going to happen to the concentration then? It's going to change, right? So since we have this addition here, in the end, we're going to take all of these moles to find out their final concentration. We're going to divide them by the new volume. In this case, it'll be 0.035. So we want to find these moles of each. I'm going to go up here. I'm going to make these conversions in my head, if you don't mind. 0.250 liters. Every 1 liter is 0.100 moles of CH3COOH. Down here, we have, again, making the conversion in my head. Every 1 liter is 0.106 moles. And we can move the decimal on this, but more math, I would rather go ahead and just put it in there. So that's the number of moles of sodium hydroxide or the hydroxide ion. And there is the number of moles of the acetic acid. So this is a reaction occurring, so we have a limiting reagent. Which of these two is our limiting reagent? .0025 or .00106. Sodium hydroxide. So that means it will get used up first. So we will have none of it at the end. Well, if that's all we have of that, that's all we can use up of this. So we end up with 0.00144. I think in the future I need to make these BSC box bigger for my writing. So what does that mean? Well, if we're subtracting that for this side, that means we are forming, if this acid is this concentration at the end, what has happened to the rest of it? It has dropped that hydrogen ion and become the conjugate base. So we get 0 plus that. So now at this point, we have this much of the acid left, and we have this much of the base left. So we know the Ka from over here, 1.8 times 10 to the negative fifth. And we know that that is equal to the concentration of the H plus and the concentration of this. This isn't the concentration. We need to divide this by 10 plus 25 is 35. So 0.0350. We need to do the same thing for this because this is what's on the bottom. HA, A minus, H plus, right? So since I had that in my calculator still, I went ahead and got 0.0411. And now this one. And we get 0.0303. And that's equal to the concentration of the conjugate base. We can put that up here. Oh, I did not maybe. Question?
Sorry, I don't understand why you divided.
By this? By this?
Yeah.
Yeah. So remember in this equation, these brackets means concentration. all of this stuff in here is moles, because this isn't an ice table, it's a BCA table. Basically, before the change, this is having a chemical reaction occur. So we can't really use concentration for that. So we changed everything to moles up here. And these are all moles. Another reason for this is why we don't have concentration with this is because we're adding these two together. So that's going to change the volume, which is going to change the concentration. So that's the new volume, 0.0350. Does that help?
Yeah.
The 0.0350. So if we take a look up here, we have 10.0 milliliters plus 25.0 milliliters equals 35.0 milliliters. But concentrations or molarity are moles per liter. So we change that to liters. Yeah. All right, so we can plug all of this in then. So we have the 0.0303, the 0.0411, 1.8 times 10 to the negative fifth. Since this is on the bottom over here, I'm going to multiply by 0.0411. And since this is on the top here, I'm going to divide by that. And we get a number that I want it to be in scientific material. I lost it, didn't I? Yep, it's all right. So retype that in. 1.8 times 10 to the negative fifth times 0.0411 divided by 0.0303. And we get 2.44 times 10 to the negative fifth. And that X, if you recall, is the hydrogen ion concentration or H3O plus, whichever one you want to write. So how can we get the pH from that? Negative log. So we hit negative log that. And we get 4.6. 1. So after we add 10 milliliters, we should be at 4.61. So that's the first point plotted on this right here. Now, another way you could do this, because we have the acid and its conjugate base, is you could take and do the Henderson-Hasselbalch. pH equals pKa plus the log of the acid over, the base over the acid, because it's lost its hydrogen here. That's the conjugate base. In this case, that would be this guy right here. And this guy right here. So if we do that, we know that the Ka is 1.8 times 10 to the negative fifth. So if we take the negative log of that, now that becomes the pKa. So right there, we already see 4.7. We know we're actually going to get 4.6 because we've already done the math for it. And we are going to add to this the log of the A negative, which is the 0.03, divided by the HA concentration, which is 0.0411. And there is our 4.61. Yes. They could be in the multiple choice, but that you wouldn't have to do all this math for it. It would say something like what goes in here or something like that. It would just give you a part of it. Yeah. Now, just to make sure we are clear, so that is by using the concentrations. This is the cool thing about the Henderson-Hasselbalch, is if you got to here and here, you can actually use this ratio of moles as well. So let's go ahead and try that. We have the negative log of 1.8 times 10 to the negative fifth. And hit enter. Then we're going to take it again. We're at that 4.7. So we're going to take that answer and we're going to add. Remember, that gets us the pKa. Then we're going to add the log of 0.00106 divided by 0.00144. And there's that 4.61 again. So either one of those will work. So if you're like, I'm done with this, I don't want to find that concentration or whatnot, you can just use the mole to mole ratio as well. All of that's there. This is the long form. This is with Henderson-Hasselbalch. It can make you stop here and you could be done. That's why it's kind of nice. Now, the next thing is we've reached actual equilibrium. We talked about that 23 before. So it says calculate the pH of the 25 milliliter sample of 0.100 moles per liter, following the addition of 23.58 milliliters of 0.106 molar NaOH. So same reaction. This is a strong acid base. So it goes forward. Don't care about the H2O again. That would just be one of anything. So again, we are using the same amount and same concentration of acid. Not the same amount and concentration of base. Oh, can't do that. 0.023 is changing that 58 times 0.106 moles per liter. Close enough to 0.0025 as well. So what does that mean? Which is the limiting reagent this time?
They both are.
You got it. So minus 0.025 minus 0.0025. Is there anybody that can actually write in these boxes? Like that. I've seen somebody that is writing. This we started with 0. We're going to add 0.0025 and we're going to have 0.0025. And here's the thing. We have that weak base. What does that weak base tend to do? Well, what's it going to do if it has this negative and everything else is equal? It's going to start pulling hydrogens off of who?
Water.
Water, right? It's going to start pulling hydrogens off of water. So that means that we need to have an equilibrium table. CH3OO negative plus that water that's there is going to end up making OH negative and CH3OOH. So with that, we then need to remember in ice tables, what are we using? Not moles, but molarity.
Molarity.
So we need to find the molarity here. So that means that we take 25 plus 23.58. That gives us 48.58. We're going to divide that by 1,000, and we're going to get, funny, mine is in scientific notation, but I think you get the idea. If it's 48.58, that's going to be 0.04858 liters. And that will give us that concentration that we start this whole ice table off with. 0.0025 divided by that gives us 5.146 times 10 to the negative second. 0.0515. And we don't care about this. After this forms, what's going to happen? Well, it's going to lose a certain amount. And these guys right here are going to gain a certain amount. And then we're going to have 0.0515 minus X, and we're going to have X, and we're going to have X. Are we making acid or are we making base? What we have here? Base, right? So are we making H plus or are we making OH negative? Right? Because the H plus is being taken up, right? By this one. So since we're making OH negative, or let's just look at it like this. Is this the same equation that the Ka is set up for? No, this is the equation, the opposite. So what do we need instead of Ka? Kb, right? So we need the Kb. We know the Ka equals 1.8 times 10 to the negative fifth. So remember that the Kb equals the water constant, or Kw, divided by the Ka. So that gives us Kb equals 5.56 times 10 to the negative 10th. So what is the Kb? Well, that is the CH3OO negative down here times the OH negative up here and the CH3OOH up here. Again, products over reactants. The Kb is telling us that we're dealing with formation of that OH negative. The Ka tells us that we're dealing with the formation of that the H positive, the hydronium or the hydrogen ion. So with this, now we can plug these numbers in, but you guys have seen this before. This is going to be equal to, maybe I don't want to do that. Maybe that'll cause too much confusion right away. I'm going to go ahead and write it all the way out just because I don't want any confusion. So the Kb equals X squared over 0.0515 minus X. The X is negligible. So we're going to take and multiply Kb times 0.0515. And then we're going to take the square root of that. And we're going to get 5.35 times 10 to the negative 6. But what is this equal to? Hydroxide. Good. So that means if I want to find the pH of this, negative log 5.35 times 10 to the negative 6, negative log of that. And then we subtract that from equals 5.27. That's the POH. 14 minus that gives us the pH equals 8.73. Now, at the equivalence point, this is why the pH is higher than 7. Because when we had that equivalence, we had the formation of some extra conjugate base. That extra conjugate base is going to pull hydrogen off of the water, increasing the amount of hydroxide ion which will increase that pH. So if we take a look at the equivalence point, like right here, we do see right here, 8.73. Boom, boom. Cool. What I'd like for you guys to do for this evening is try number 4. And if you would, try this operational exam problem from 2002. Questions? Hopefully I went slow enough for you guys today. I know that like everything says that this is one of the more difficult topics. Basically because it's like